Hello everyone, welcome back. I am Siddharthan. In this video, we are going to build a house price prediction system using machine learning step by step. This is not just about training a model. We will go through the complete workflow from understanding the dataset and performing exploratory data analysis to data pre-processing, model building, model selection, hyperparameter tuning, and proper evaluation. I will also explain why each step exists so you understand how a real machine learning project is built and not just how to run the code. And this project is part of my complete machine learning bootcamp that I launched on Udemy recently. And I am sharing this video on YouTube to give you a clear idea of the depth, structure, and teaching style that I follow throughout the course. If you like this way of learning and want to build more end-to-end machine learning projects like this, I have given the link for this machine learning bootcamp in my video description. You can check this out. So this course is 66.5 hours long. There are 5 assignments and there are a lot of quizzes that you can attend, and there are about 128 lectures, and all these videos will be detailed and structured. So check this out if you're interested. Now let's get started with building this house price prediction project. Welcome back. In this video, we move into our fourth machine learning project, and this is where we transition from classification problems to our first full-scale regression project. In the previous three projects, we focused on classification tasks, building intuition around model training, evaluation, and improving performance step by step. Now, we apply those same ideas to a much more realistic and commonly used regression problem, and that is house price prediction. In this project, we will work with a real-world housing dataset and build an end-to-end regression pipeline. We will start with a detailed exploratory data analysis to understand the features, distributions, relationships, and potential issues in the data. From there, we will move into proper data pre-processing, including handling missing values, feature scaling, and preparing the data in a way that actually makes sense for regression models. We will then compare multiple regression algorithms using model selection, discuss why certain models perform better than others, and go beyond a single baseline by applying hyperparameter tuning in a structured way. Finally, we will evaluate our models using appropriate regression metrics and interpret the results so that we understand not just which model performs best, but also why. By the end of this project, you will have a clear blueprint for how to approach real-world regression problems from raw data all the way up to well-tuned evaluated model. So let's get started with the hands-on part. I've created a separate directory called as 15 underscore 4 house price prediction, and I have created a virtual environment over here. You can use that same python -m venv space .venv command to create your virtual environment. And let me just like select the kernel over here. So I'll select this .venv that I have. Okay. And the data set that we will be working on is this California house prices data set, and the name of this file is housing.csv. And this is the Kaggle link. I'll share this dataset file as well as the notebook in the material section of this video. You can download from here, or you can also access the dataset and look at the description from this link. Let me show this Kaggle site to you from which I have downloaded this data. So this is our California housing prices dataset, which contains median house prices for California district derived from the 1990 census. So this is the context that you can go through and all that, and these are the columns that we have. So we have longitude, a measure of how far west a house is, higher value is farther west, and so on. So basically your longitude value and latitude value. What's the housing median age? Median age of a house within a block, a lower number is a newer building. Basically, like, how many years kind of went by after creating the house. So similarly, we have total rooms, total bedrooms, population, and so on. So the main target column that we are interested in is this median house value. So median house value for households within a block. So this is what we are going to predict. So median house prices, and this is the data. So you can sign up to Kaggle and you can download this data set from here, or you can also download it from the material section as I said. So this is about the data, and this is the process that we will follow. So once we load this data set, we will perform exploratory data analysis with visualizations and all that. And then we will pre-process this data with appropriate pipelines that includes missing value imputation, feature scalings, and all that. And then we build a baseline model. So we are building this baseline model so we can clearly see how much improvements we are getting in the optimization step that follows. So once we have the baseline model, we then move to a proper model selection with cross validation that tells us which model performs better for this particular dataset. And we also tune that specific model using research CV and then we finally evaluate it and also make sure that there is no data leakage. And finally, we build an inference pipeline where a person can give new house price data set and we make a predictions out of this. So this is the flow that we will follow. So the first step is, as we always do, is setting up. So here we are installing the required libraries: NumPy, Pandas, Matplotlib, Seaborn, and Scikit-learn. So we have NumPy for any array related or NumPy array related applications and calculations, and then we have Pandas to read this CSV file into a Pandas data frame, and then we are importing Matplotlib and Seaborn for plots and graphs, and the next part is for our data pre-processing. So from sklearn.model selection, we are importing this train test split. We would split this original dataset into training data and test data. And on this training data, we would do all the model selection, cross validation, hyperparameter, and all that. A test dataset, let's call this as global test dataset, will be set separately, and we won't touch it unless like we kind of reach that final evaluation. So this training data will be used for like our optimization and every places, where we would also separate a validation set, and the test data set is like separated out, and we just like use it for our final evaluation. And then here we are using a k-fold for our cross validation. So this is for that. So k-fold and cross validate, so that we can report a better metric compared to a single accuracy score, or like your error metrics like mean absolute error. So instead of doing that on one test set, we are going to perform cross validation so that we can get a more reliable test score. And then we have grid search CV for hyperparameter tuning. So and then we move to this from sklearn.pipeline, we are importing this pipeline. So the importance of pipeline is that instead of doing these feature scaling and your missing value imputation and model training separately, we are going to chain all these things together in a pipeline so that it's easily scalable, and you can simply call this in order to perform these multiple steps. If we don't use a pipeline, right, you would need kind of like a separate missing value imputer. You would kind of fit and transform your data, and then you would need a standard scaler, and then you have a model. So you call all these steps separately. Rather than that, we build this scalable system where we create a pipeline and chain all these entities into a pipeline, and we just call this once and all the process just happens there. So that's the importance of pipeline. So I'll explain a bit more about this when we use this. And then we have this sklearn.compose. We are importing column transformer. So this is an interesting thing, and I think we haven't used this in our previous projects. Think about this. Categorical columns, if they have missing values, they should be handled differently. Let's say they have to be replaced with mode value, right, the most frequent value. Whereas for your numerical values, the missing values can be replaced with median, right? So this is the core idea. And we know that we apply standard scaling, but the standard scaling should happen only on our numerical data set and not on our categorical features. So these columns should be handled separately. Categorical columns should be handled separately, and numerical columns should be handled separately. And this column transformer is going to help us to do these different kind of pre-processing under a single pipeline. So this is the advantage of this. Basically, numerical features requires one flow and categorical features requires some other flow for pre-processing, and then this data has to be joined, and then we train our model. So column transformer just helps us to do this in an easier way. And then we have standard scaler from sklearn.preprocessing to scale the numerical features so that the feature can be in the same scale. And then we have one not encoder. So this data set has a lot of numerical columns, and there is one categorical columns which is present in the form of strings or categories. So we use one not encoder so that we can transform this column into one not encoded columns. So please refer to our previous section video where we have discussed about this categorical columns encoding in our pre-processing section if you want to just like revise the concept of one not encoding. So next we have simple imputer. Simple imputer we are importing from sklearn.impute, and this is used to replace the missing value with median value or your mode value. And these are the models that we will be using for our model selection. From sklearn.linear model, we are importing linear regression, ridge regression, and lasso regression. And then we have this from sklearn.ensemble, we are importing this tree-based models, random forest regressor and ist gradient boosting regressor. And we have discussed about this ist gradient boosting regressor in the previous video as well. So it's a sequential tree-based model where it tries to keep building more trees, where the mistakes made by one tree, the next tree is it's trying to resolve those mistakes. So that's how this is going to work. So these are the two ensemble models and tree-based models that we will work with. And then these are the metrics that we are going to use. From sklearn.metrics, we are importing mean absolute error, root mean squared error, and R squared score. So these are the three things that we are working with. So these are the required dependencies for our project. So let's run this. So I already have this code ready for this data analysis and mainly for data analysis for our exploratory data analysis and visualization. I already have this code ready because all these code are pretty much what we have discussed in the previous section and the previous project videos. So let's not kind of spend a lot of time in rewriting this code. But as we move to this pre-processing step, I will just like type in every code, each and every line, and then I'll explain you this in detail. As we have just like talked about these EDA several times, I've just like already did this code and I'm going to explain this to you. Right. So the next step is configurations. So just like setting up some notebook level configurations. So here we are setting this thing as display max column. So when your data frame has several columns, when printing, pandas is going to truncate few columns, and we don't want that. Let's say if you print a head of a data frame, you want to see like all the columns. In that case, you can say display.max columns as none. So this tells pandas that no matter how many columns the data frame has, just display all those things when I'm printing something. And then we have display.float format lambda x colon dot 3f. So this is again the same thing that we have discussed earlier. So when there is a larger decimal value, when we print it, pandas would just convert it into scientific notation with e power 3 or e power 4 and so on. And if you don't want that, if you just want to look at the raw decimal value, you can just configure this. So this is saying pandas that the float format or the float values should be displayed in in the format where it has 3 decimal values and don't use any scientific notation. And this sns.set theme, SNS is our Seaborn library used for plotting. And we are saying that the style is dark grid, like how the grid color should be and so on. So it is like the theme of that. And then we have plt.rc params update. So this is like the font details of the plots, like you have x-axis labels, y-axis labels, title and so on, right? So this just tells that what's the font size for all those plots. So title size, label size, X and Y label size, and so on. Simple configuration details. And once you set this up, this will be kind of followed for all the other cells that are going to come later in this particular notebook. So this is a notebook level configuration. And then we are setting up a random state of 42. So this is going to help us get reproducible result. So every time you run this code, run this notebook, you are going to get the same result if you set a particular random state value. So that's about it. And then we are kind of like giving this CSV path. So CSV path, just like you can give the name of the file, this housing.csv, if you have this dataset file as well as your notebook in the same directory. If not, you have to basically give the entire path. Let's say your notebook is in a different directory and your housing.csv is in a different directory, then you have to give your entire path in the CSV path. And you can just like simply update the path if you are working on a different data set. You can use some other regression data set with this notebook as well with some minor tweaks. So if you're working with a different insurance cost prediction or something, just update the CSV path over here and that should do the trick. And then here we are mentioning the target column that we have seen in Kaggle. Medium house value is the target column. So these are kind of like the configuration details that we have over here. And the reason we are doing it here is, if you don't set up your target column and CSV path and so on, we end up using the actual names in the later part of the code. Let's say I'm kind of trying to build a matplotlib plot and I'm mentioning this median house value. And now there are like several places where we have hard coded these target values in those cells. Now when you use this notebook, just copy this and use it for a different data set. You have to change this name in different places. Instead, if you have these configurable things as your target column, CSV path, random state and so on, you can simply update this top cell and that will be kind of like propagated to the other places, because we wouldn't have used this kind of column name exactly. Rather than that, we would have used this particular variable. So that's why we are making these things configurable. So this is our next step. And then we have like simple aspects. So here we are reading this CSV file by providing the CSV path over here using pandas pd.readCSV and creating a data frame inside this variable called as df. Here we are printing the shape of the data frame, and this data frame has 20,640 rows, which is a pretty good number. And then there are 10 columns. We can also print the first 5 rows, the sample of this data, using this df.add, which is going to give you the first 5 rows of this data frame. So we have longitude, latitude, housing median age, total rooms, total bedrooms, population, households, median income, median house value, and ocean proximity. So So these are the different columns that we have, and this ocean proximity is our categorical variable, and the other features are basically numerical variables. So this is about the basic details about our data set. Now let's move to the next step, which is exploratory data analysis. Here we are going to understand about the data in a better way. I'm running this df.columns, and this is going to print all the column names that we have. So later, if you want to just quickly check the columns in your data, you can simply use this code df.columns. And here I have the column details. This is basically what we have seen in this Kaggle site. I've just like copied and pasted it here so that you can just like, if you have some doubts about a specific column, you can just go through this. So this as those column details, basically column description. And now we are getting this basic dataset overview using df.info. So we know that df.info shows how many columns are there. So it says there are totally 10 columns and there are 20,640 rows. And this tells you how many values are present. So non-null values means the values that are present. Okay, null values are missing values. So if this number matches this number, then there are no missing values. So that's the idea. So for most columns, the number is 20,640. So 20,640 non-null values means all these values are present for longitude. But if you look at this total bedroom column, only this column has some missing values in it. So 20,433 values are present. So what it means, like about 207 values are missing. So that's what it says. So, and it also gives you the data type. So we have all these columns as float data type, which is basically your decimal value, and your ocean proximity is object because it's present in the form of string. To be precise, it's a categorical column, so that's why it is present as object. So this is where we would kind of use one not encoder to convert this object data type into a numerical value in a encoded format that the model understand. So this is about it, right? So we don't need this. Let's move to the next step, but we don't need this target call variable as we have already configured the target column, this configuration space. So let me just like quickly delete this. This is redundant. Here I can just print the target column. All right. So what we are doing here is, for our processing, it's easier if we can get a list of numerical columns as well as categorical columns. So numerical columns we can select by saying that take this data frame, select all the columns where the data type is a number. So we say include all np.number, that means numpy.number. So this would include all the integer values and floating point value. Think about this. It will take this data frame and include all the number data types, which can be your integers or floating point values. So get the column names and convert it into a list. So next step is, similarly for categorical columns, we are going to take this data frame and select the data type wherever the data type is an object, and similarly create a list. So here numerical columns are longitude, latitude, and all the way up to median house value, and categorical column is ocean proximity. So you can think that you could have easily manually done this, right? You could have manually typed in longitude, latitude, housing median age, and so on in numerical columns list, and you can manually typed in categorical value as categorical column as ocean proximity. But the thing is, if you are working on a different data set that has hundreds of columns, then we won't be able to do that manually. So this is a better way to get this programmatically by just detecting the data type and printing it. So here we have numerical columns as these things, and our categorical columns as ocean proximity. But just remember that these are not my features. This also include my target column, which is my median house value. So that's one thing to remember. So now let's analyze the amount of missing values in our column. So we can use this df.isna.sum. So this is going to print the presence of any missing values here. So as we have already checked in this df.info, we can see that there's total bedroom columns as 207 missing values. So we have to impute this like when we are working on this. And this is a numerical column, numerical feature. So we would replace this missing values with median value. You can also kind of use mean value for replacing this, but if there are outliers in your column, then mean is also affected by it. So we use median so that median is also not affected by outliers. So we replace those missing values with median value. So that's one thing that we can keep in mind. Now we have done this for other projects as well. We need to check the presence of encoded missing values. Sometimes what happens is, the person who is preparing the data, there is a chance that they wouldn't leave a particular row or a column as a missing entity. So here, let's say we have 20,600 rows or something, and 32 columns, or sorry, 12 columns something was there, right? Now instead of leaving it as a null space, which basically means don't write anything on that CSV. Let's say there is a missing value in this data set. So how it would be is there won't be any value over here. So it would be like this. Sometimes people won't do that. The person who is curating this data, who is collecting this data, can replace this value with a question mark, or they can replace this value with some number like -9999 and so on. So these are basically missing values, but they are encoded for better data storage and having a consistent format. So instead of having like a null string, they can just like replace it with some placeholder values. So we need to understand that we don't have those placeholders, and sometimes when you check this is na or is null, there is a chance that those kind of placeholder values are skipped. It just like checks the presence of null values or null strings, so it won't be detected. So in those cases we have to make sure that no placeholder values are used for this missing values. So for that, one way to detect this is, and sometimes this can reveal, this can reveal those missing values. So we are taking the columns of this data frame, iterating over each of this column, and trying to print the most repeated columns, top 20 repeated values of each of this column. So what I will do is, when the for loop runs for the first time, we take this longitude column, we find the top 20 repeated values, and we print it. So basically get this column, get the value count. So this is going to give you the number of times a particular value has been repeated. And now we are focusing on only the top 20 values. So let me run this, and this is my output. So this is truncated. So I'll just open this in a text editor. And yeah, so for longitude, this is the first, mainly like the top 20 repeated columns. For latitude, this is the top 20 repeated columns, and so on. So we have like all these values. Now what happens is, let's say out of 20,000 values, this is like numerical value -118.310. So this is as like repeated 162 times. Let's say there is a placeholder value that has been encoded for missing value space, and let's say question mark is used to replace that, and we can consider that there were uh, 500 missing values in your data. Now there is a high chance that if the missing values are present, it would appear here saying that this question mark has been repeated 500 times, or this a strange number like 1 lakh, or 1 million, some large number is present over here, which sometimes represents this placeholder for those missing values. So basically the idea is, we take each of this column, find the top 20 repeated values, and trying to see if missing values have been encoded with some placeholder value, and this can sometimes reveal it. Again, it's not like perfect, it may not be able to identify all the missing values, because sometimes the missing values may not be like the top 20 repeated values. In that case we can miss it, but more often than not this would reveal the encoded missing values. So always when you're working on some data set, make sure that you're not relying only on this df.isna or df.isnull. You also kind of use this value counts to understand the presence of any encoded missing value. So that's a very big takeaway. So this is our final inference based on our missing values analysis. So we saw that total bedroom column as like 207 missing values. So I've just like entered it over here. Total bedrooms as missing values, and later in our pre-processing step, we can impute those missing values with our median value. And the important step is, we shouldn't take this entire data frame and replace the missing values with the median value. So that would lead to data leakage. First, we have to split our data into training data and test data, find the median value for total bedrooms column in the training data, and now replace all the missing values both in your training data as well as your test data with this median value, that is basically that we got from training data. So this prevents data leakage, so just keep that in mind. And now we are checking the presence of duplicates. So we are saying duplicate mask variable is equal to df.duplicated. So this is just going to give you a matrix of Boolean value, true or false. And we just like count how many true values are there. So it's mainly basically used to identify whether there are some rows that are like basically repeated, or like exact copies or duplicates. So this is going to reveal that. And here we get this number of duplicate rows as 0. In case for some other data set, if you have any duplicate values, you can drop those duplicates using these two lines of code. Just uncomment these lines of code and run it, and that will drop those duplicate values that are present. Then we can get the descriptive statistical measures like your mean value, median value, percentile values, and so on. And this is very helpful to understand whether your data is skewed and all that, what's the minimum value, maximum value, and so on. So this is going to be interesting to see. So we have this longitude, latitude, and median house value, which is like pretty important column for us. So we can see like the minimum value is this, right? So it's like 149. Oh no, it's 14,999. So that's my minimum value, and maximum value is 500,000. There is one nuance here. I'll talk about it in a bit, but yeah, let's just remember that this is our minimum value and maximum value. You can also just do a transpose of this df num calls dot describe. Again, describe, we don't do that on categorical column, so we just like do it on the numerical column. So I'm just like saying that take the data frame, do this describe only for my numerical columns that I have identified over here. If you see this, so that's what is happening, right? And then we can just transpose it. Again, it's not going to do anything different. It's just going to flip this rows into columns and columns into rows, so that it's kind of in a better viewable way. So all these values are for longitude, all these values are for latitude, and so on. So this is what we have. We can just like look at this comparison of mean and median, and that would kind of like give this comparison of whether the data is skewed or not. If you see this 50th percentile is my median value, so it is 179700, and this is my mean value. So mean value is larger than median value, so there is a chance that the data is skewed, and you can just like refer those other columns as well, and most of the columns will be skewed. We can just like verify this in our data visualization code. So first is we can draw a count plot to analyze our categorical column, and the categorical column we have is this ocean proximity, right? So that you can directly draw a plot, but as I said, I want this code to be scalable and be useful for other data sets as well. So if this categorical columns in a different data set has 5 categorical columns or categorical features, this code would just like run this for loop through these different columns, and it's going to draw a plot. Okay, so here we only have one column, which is your ocean proximity, so it's going to draw a plot. But if you have 2 columns, 3 columns, or any number of columns, here we are iteratively drawing these count plot for all those categorical columns. So we iterate over this categorical column, set up the figure size. So 10 is the horizontal size and 3 is the vertical size. And here we are creating a count plot, passing the name of the column. So call basically takes the name of this column that we provide from this list, and the data is data frame. So it's going to take this data frame, select only the column that we provide here. So in this case, the column will be ocean proximity, and we give a title using this f string saying distribution of call, where in this case it's distribution of ocean proximity, and this is what you're seeing here. And we see this. So these are the different categories we have over here. So totally there were 5 categories. So we have near bay, the other one is like less than 1 hour from ocean, and some houses are like inland, and then there are like few near ocean, and island is like probably doesn't show some values, maybe the numbering is like quite low. You can also get the actual numbers using this df of maybe let's do this for column in cat calls. We can do a df of call. Similarly, we are just like iterating over it, so that if there are multiple categorical columns, this would print it on this. So it says the top repeated value is this 1 hour from ocean. Again, we can see this in the graph as well. So the exact number is 9136 out of this 20,000. Inland there are 6551 values. Near ocean there are like 2658. All these are individual house numbers. So it's like 9136 houses are less than 1 hour distance from this ocean. Inland 6551 houses, and so on. Island has a very little number of 5 kind of like houses, but we can keep this. We don't have to drop this just because it is like present in a very lower number. That's okay. I mean, because it represents like real world scenario, right? So we can just like keep it as is, but this is the distribution for our categorical column, and of course there is some imbalance over here. Now let's move on to this next one. So how the distribution is looking like in our target column. So we know the target column is important for us, right? So we can just like go through this to understand that. Let me just replace this with of this. Let me use this target column. So this is what I was talking about. So if I just like keep it, let's say I'm not using this target column variable, and in all these places, if I use this exact target column name, what happens is we have to replace the column name everywhere if we are working with a different data set. So it's better if you use a variable like this, and if you're working on a different data set, simply update the target column name over here, and that would do the trick. So that's the reason we are going with this configuration based approach. So yeah, I hope you kind of get that right. So here we are drawing a histogram plot, so a distribution plot with this particular column, target column, with let's say 40 bins, and there is a KDE. KDE is this kernel density estimation. That's going to draw a smooth curve on top of these bars, giving a title and X label and saying plt.show. So we have values from this, let's say 100,000, 200,000, all the way up to 500,000. This is a right skew. That means like we have the tail on the right side. The main important things that we need to understand from this data is most of the data are situated in this range, right? From this 100,000 to 200, 250,000 range. And this is just similar to the real world scenario, right? Let's say houses in the lower price range to mid price range, more people would have those houses, and let's say more expensive and luxurious houses, number of people who own that houses will be lesser. So that's what this graph basically means. So there are more houses in this particular price range. So here we took this median house value and plotted this. So there are more houses in this range and there are less houses in this range. So this is what it means. And now look at this value, and this is very important. So here we have so many houses that are of the value, let's say this is 500,000, right? So it says that this data set has a lot of houses that are priced at that 500,000. Now, this is actually not true. This is the upper cap for our data set. What it means is there is a chance that in our data set, let's say the actual price of the house is not 500,000, let's say it's 1 million. Now, the person who has curated this data, there is a chance that they have capped this larger amount to 500,000. So any house can have a larger price, or like the max value can only be 500,000. So it can be the actual price can be 1 million, 2 million, or 3 million, but this data has been capped. So if you train your machine learning model, what happens is your model also has this limitation that it cannot predict beyond this maximum price, because your model is as good as your data. So what happens is it wouldn't be able to correctly identify the houses where in real world it can be 1 million or 2 million, but it wouldn't be able to give those values because your model is trained on a data set that has some higher capping in it. So this large amount of value in this last column represents that there is a upper cap in this data. So what happens is your R squared score can be low. So we have discussed about this R squared score in our evaluation metrics for regression, where we said that R squared basically tells you how well your model can identify the variance present in your data. And when you introduce a upper cap, the variance is reduced. So originally you should have like houses that are in 1 million, 2 million, and so on. So there is a lot of variance or variation in your data, but this variance has been dropped because we added a cap. So because of this, we cannot expect a higher R squared score for our model. So this is a very important insight that you need to get. So if you don't do this exploratory data analysis, what happens is you might kind of like try a lot of different things, but you wouldn't be able to optimize it better. Your R squared value can be still low, and this problem comes in. This is why we have to do a proper EDA to understand the data better, and based on that we can infer that this is why my model is going wrong and this is what I have to do differently, and so on. So that's one thing that we can remember. So this is the inference that we are getting from this distribution that we draw from this target column. You can also verify this from this value counts. So we can see that topmost repeated value is this 500,001, and 965 houses are in that price range. So which basically tells us it's kind of like a upper cap, whereas other values are not repeated like beyond this particular rate, right? So that's one thing that we can kind of remember. So there is a upper cap, and because of that the R squared value cannot be increased after a certain value. And because of this, what happens is the model may tend to make mistakes at this particular place. So it can work well in predicting the house prices that are in the range of this 100,000 to 250,000, but if we give more house prices that are in the range of this 500,000, the model gets confused because the data is not very clean in this range, in this particular range. So it kind of won't give you like a better result, so the error can be there. So that's one insight we can get from this. So next is a distribution plot for all the other numerical columns, and now let's discuss about it. So in this part of the code, we are going to iterate over all the numerical columns and draw histograms for this. Just like the way we did for target column, we are going to do it for other columns as well. And again, as we have done in the previous video, instead of doing that like one after the other, we are going to create one plot, and within that we are going to have these distribution plot as subplots. And look at this font sizes, font size of the x-axis, y-axis, and your title and all that. So all these are basically derived from the parameters that we set in our configuration space over here. Okay, so this is where it is coming from. So let's go through the code right now. Come back here. So we are saying that I need a 3 into 3 plot. So you see like these three plots, basically 3 rows and 3 columns of this plot. So this is what we are providing it over here. And the overall size should be horizontal 8 units and the y-axis is 6 units. So that's the size of this entire plot that you see over here. And then we are creating this axis, and in this axis we are going to iteratively plot this numerical columns using a ist plot. So we take one column at a time and plot it at that particular position. So first we plot this longitude column here, latitude column here, and so on. So this is the code about it. Now look at this. We have two peaks over here in longitude as well as in our latitude. So what this says is more houses are present in these kind of odd spots. So let's say we have this California state. I think it's a state, but I'm not exactly sure. I think it's a state. So let's say in California state, there are these two places where the amount of houses is more. They can be like the main cities and so on. So there is a chance for that. So we have those peaks in this longitude and latitude. And then we have this housing median age. So age is that, how many years kind of went by after like, building that house. So lesser number means it's a new house and so on. And here also you can see a peak. So there is a high chance that there is also a upper cap over this particular place, just like the way we saw in our median house value. So we have this particular plot, and almost other plots there is like a right skew. So what it says, this is like the total rooms and so on. So we can say that most houses have like lesser number of rooms, and only less houses have like higher number of rooms. So that's about it. And then total bedrooms, population is basically it can be an apartment kind of a thing, or where people are like kind of sharing a household and so on. So it counts like how many people are there in that particular household or in that particular community and so on. So this is that households and so on. So this represents like the total bedroom overall, total population in that and so on. And then we have median income, and this can have a pretty high influence. So this is because let's say that this represents the income of the people in that particular region, or basically we have a set of houses, and what's the median income of the people kind of owning that house. So there is of course a chance that people who are making a large amount of money would probably buy houses that are kind of expensive, right? So we can also see probably like a correlation where if the median income is high, the house value might also be higher, and that's pretty logic. So this is what this distribution plot gives us, and it says that most of the columns are skewed, and we see this upper cap in our median house value and our housing median age kind of like column. So those are the two things. We are kind of using like a similar code to draw this box plot so that we can identify those outliers. So we have this longitude, latitude, housing median age. So these doesn't have any outliers. These circles that you see over here are outliers. Again, in this data set, the outliers need not be kind of errors or measurements per se. Errors, they might not have to be errors. They can be like actual values. So we don't have to replace this with median values at all. So when let's say the outliers are not logical, let's say they represent some mistakes in the data, in those cases we replace these outliers with median value. But this can represent like real world scenarios, we kind of can leave it as is. So here we can see like most of the values are in this particular 500,000 range, because we know that there is a upper cap over here, and all these values are termed as outliers in this data. So this is our outlier analysis, and based on this distribution and outliers, we don't have to make any specific changes or handle this outliers, because if you just replace this outliers, there is a chance that the variance in the data is going to drop. So that's a problem. And again, the other thing is the outliers can represent like actual scenarios, so we keep it as is. In the next step, we can draw a correlation heat map that gives us the relationship between different columns. So we set the size of this plot, we use this sns.heatmap, and that's going to create a heat map. And we are taking only the numerical columns, as again this kind of makes sense to do only on numerical columns. So we are getting the correlation matrix, and then just like setting up some configuration saying that annotations is equal to true. So it says that the correlation value is 0.9, 0.8 and so on, and this represents the color map to be cool warm, center as 0, giving a title, and plt.show. So let's run this. So center will be at this 0 will be our center part of this graph, and then yeah, we have like all the values over here. So this gives you how the values are correlated. So we can see like a minus 0.92, strong correlation between this longitude and latitude. I mean strong negative correlation between longitude and latitude value. Look at this center part. You can ignore this diagonal part, because diagonal we are just comparing. If you take this box, right, so from this diagonal, let's say we take this first box, we are comparing this longitude with longitude, so it's basically the same value. That's why you're getting perfect I correlation of +1. Just ignore that, but look at this 0.93, 0.x is 0.92. So there is like I number of correlation, there is a I positive correlation. It can be evident once you look at the column names. So if you take the 0.93 square, or this particular box, on y-axis we have total rooms, and this x-axis we have total bedrooms. So this is why it kind of like highly correlated, right? So one of the rooms may not have to be a bedroom, but all the bedrooms comes under this total rooms, right? So these two columns kind of represent a similar idea or similar information. Similarly, when the number of rooms is higher, the number of people who are going to stay in that house is also going to be higher. Similarly for households and so on. So that's why we kind of see like a higher positive correlation in these columns. And if you look at this thing 0.69, and again the same values, these are basically, so we have median income and median house value. So we have 0.69. So there is also a high correlation, not as high as 1 or 0.9, but there is a high correlation. So what it says is, if the median income of that person in that house is higher, there is a chance that the price of the house is also going to be higher. So there is a positive correlation between this median income and our median house value. So this is a very good representation. Again, we have talked a lot about this correlation. So we know that this value ranges between +1 and -1, +1 being I positive correlation, and -1 means I negative correlation. When your data has this I positive correlation or I negative correlation, this leads to a problem called as multi-collinearity, where we kind of drop one of the columns. Let's say here one column is, let's say, highly correlated with two other columns. In those cases, we would just keep one column and drop the other two, because linear models can get confused with that, because these columns are giving the same information. Whereas tree-based models are not that much affected by this. So what we can do is, for this particular data set, for baseline, we can just use a linear model without dropping any columns. But for our model selection and for hyperparameter tuning, we can kind of try both linear regression, lasso regression, and everything, but also try our random forest classifier and your east gradient boosting regression, which are basically like tree-based models that are kind of not that much affected by this I correlation. So that's like one call that we can make based on this correlation heat map that we are seeing. So this is the main takeaway here. So we see like I positive correlation between these different rooms related columns, and tree-based model can work better for this. And now we can also take this median house value and compare the correlation. Basically, this would just give this particular values. It's like saying, taking all these features, how these features are correlated with my target column. So that's about it. So correlation with target column. So take all the numerical columns and compare it with the target column and sort it in ascending order. Let's run this. So ignore this. So we are getting this one because here we are comparing this median house value with that same column. So it's like comparing the target column with the same target column. So that's why it's one. So it's basically this one that you're seeing over here, and the other values are important. So this is not important for us. If you see this median income, it has a high correlation of 0.688, which is the 0.69 that we see over here. So it says that as income increases, we can say that the price of the house also increase. Apart from that, the correlation values are closer to zero, so there is not much like higher correlation over here. So this is like one insight. So these are the key insights. These are mainly what we have discussed in this EDA that we did so far. So the data set has numeric plus one categorical feature, which is ocean proximity. Only total bedrooms as missing values, which we will later kind of handle in our pre-processing step. So target column is median house value, and this is like right skewed and it is capped, so that 500,000 cap. And several features show strong skew and outlays. Median income is the strongest predictor. Strongest predictor as in it shows like high correlation with our target column. So high multicollinearity among room and population related features. So these are our key insights that we got from our exploratory data analysis, and this is our pre-processing plan and evaluation plan. So median imputation for missing values. So we have missing values in our numerical column, which is I think total rooms, right? Total bedrooms. So there we can just like replace the missing values with median, and we would apply this one not encoding on the categorical features that we have, which is our ocean proximity. And then we apply this feature scaling, and this feature scaling is required for linear models, but tree-based models, it doesn't get any advantage. You can either do standard scaling, or you don't have to do standard scaling. So that's possible. So that's one thing. And here we are going to use pipelines to chain all these pre-processing steps, missing value imputation and the standard scaling, to kind of do this in a single chaining process. So we will use pipeline for that. And then we would create a baseline model without any cross validation or optimization and everything. Later, we would kind of use model selection where we would try different set of models. And once we find the best model for this use case, we perform hyperparameter tuning on top of this. And then we kind of perform this evaluation on this, where our primary metric is going to be RMSE, which is root mean squared error, and secondary evaluation metric will be, so secondary metric will be your mean absolute error and R squared error. Root mean squared error, we are using it because if the model is making larger errors, then root mean squared error value is high. Basically, it penalizes larger errors. We are kind of using this RMSE as the primary metric because we know that there is a higher cap in this target column towards the higher end. So in these places, the model can, make more mistakes. So to penalize that and to say that, you shouldn't make mistakes over here, we are using RMSE because as the errors are squared in root mean squared error metric, it's going to kind of like give more penalty when the model makes like larger errors. So here the errors will be smaller, whereas here the errors will be larger. If you use a mean absolute error, then all the errors are treated equally. But as we have discussed in our evaluation metric video for regression, mean squared error and root mean squared error are used where larger errors are like kind of more problematic, and it gives a higher penalty for these larger errors. And we know that because of this capping, there is a chance that the model can make mistakes here as there is a higher cap here. So that would be our primary metric, which is root mean squared error. And then mean squared error, mean absolute error and R squared score will be our two other secondary metrics. And then we would finally evaluate it on the test set. As I said earlier, we will keep a global test set that has not been used for model optimization, cross validation or anywhere. It will be used only for our baseline models evaluation and then our finalized tuned model evaluation. So we will have like a separate model so that there is no data leakage. So data leakage is a bigger issue. So we make sure that there is no data leakage that is happening. So that is the pre-processing and evaluation plan, and these are the insights. Now we can move to the data pre-processing steps. Okay. So the first step in data pre-processing is separating our data into features and target. So let's understand that. So here I'll add a comment saying separate features and target. So let's say x is equal to df.drop. So we are going to drop the target column and have the remaining columns here. So target columns is equal to target. So let's pass it over here and let's say y is equal to, so x can be uppercase and y can be the lowercase as per the conventions that we usually use. And let's pass our target column. So basically we are taking this entire data set, dropping the target column and saving the remaining features to x, and the target column will be saved in this variable called as y. So let's run this. You can also try printing the first 5 rows of x and y like this. So I'll say x dot get. So this is the first 5 rows here. And then I can say y dot get, which is the corresponding house prices for these 5 data points. So the first data point or this first house have this price, second house have this price, and so on. So next step is we are going to separate this data into train and test split. So in this pre-processing, we are initially doing this train test split so that all the other pre-processing steps like scaling, your missing value imputation will happen after our train test split so that we can avoid data leakage. Data leakage is a problem where information from your test dataset is accidentally leaked into your training data. So it's like your model having a look at your test data before the evaluation. So what would happen is like it's kind of your model having like a leaked question paper before exam. So we shouldn't kind of like allow that. So that's what data leakage is, and we have to make sure that we do this pre-processing after train test split. So that's the reason for this. So here I'll say this is a train test split. So here I'm going to create some variables. So I'll say x train, x test, and then y train and my y test. So these are the 4 arrays. So here let's use this train test split function that we have imported from sklearn.model selection. So here we have to pass our x, y, and the test size as 0.2. So I'm passing my x and y. Test size 0.2 means out of our 20,000 data set, 0.2 represents 20%. So 20% of data becomes test data set, as this is the test size, and the remaining 80% will become your training data set size. And then I'll add this random state value. This is for reproducibility. So random state value, we have provided the value as 42. So this means like if you use the same number 42 for random state, your data will be split in the same way that my data is splitting, and because of that you will also get the same score from the models that I am getting. So that's the reason for this random state. Of course you can use other models as well, but again it's simply for reproducibility, not any critical features or like importance. So this is our train test split. So my entire X and Y data will be split right now. So Xtrain will be my training data features, and the corresponding target, the house prices, will be saved in my Ytrain. Xtest represents my test data features, and the corresponding labels or my house prices will be saved in this Ytest for test data. Okay, so let's run this, and then we can just simply print the training shape and test shape. Let me just like quickly do that in a moment. Right. So we have the training shape as 16,512, which is 80% of our original 20,000 rows, and 20%, which is 4,000 rows, it will be our test data set size. So this is how you can first separate your features and then split your data set into training data and test data. Now comes the important part of setting up our pre-processing pipeline. So I'll create a markdown cell and say pre-processing pipeline. Call this as pre-processing pipeline, and let's make this bold. Right, so now I'm going to create two variables. One is numerical features and the other one is categorical features. Of course you can use that same num calls and cat calls variables that we have created earlier, but let me just create a separate one for like better access or remembrance. I'll call this as numerical features is equal to, I'm going to take this X and say select data type. You can also take this X train and Y train as well, so that's also fine. So I'll say select data types include is equal to np dot number. Maybe let's just take this from X train for better format. Again, it's the same if you use your what you call X as well, but let's have it this way. So we have this include np dot number. So all the numeric columns will be saved in this numerical features. So we have to take columns. So when you just like do this right, numerical features is equal to xtrain dot select data types include np dot number, and then print your numerical features. So it's going to basically create a data frame that has only your numerical features. Your original xtrain has numerical features as well as one categorical features. Now I want only the names of these columns, all those numerical columns. So we have to get this columns. So it would give you like the list of all the numerical columns except for this ocean proximity, as this is a categorical columns. And for better processing and operations on this, we can convert it to a list. So now when I run this, it's going to give me this numerical features in the form of a list. Similarly, we have to get our categorical features. So I'll copy this line, paste it over here, and just update this. So instead of this numerical features, let's call this as categorical features. And then here let's say select the data types. Instead of saying include, I'm going to say exclude. So I'm not going to change this number. So here I'm saying include all the numerical features into this list called as numerical features. Okay, and categorical features is basically all the columns excluding my number. So it's nothing but your ocean proximity column, nothing complex there. So in the first place I'm saying include all the numerical columns. Here I'm saying exclude all the numerical columns, so the remaining categorical columns will be saved. This will work correctly even if you have like more number of categorical columns and any number of numerical or categorical columns. So this code would still work, and that's the reason we are like kind of doing it this way. So here let's say that numerical features is this, and similarly let's print our categorical features. The reason we are doing this is categorical features should go through a different set of pre-processing steps, and your numerical features should go through a different set of things. So that's the reason. So I'll say categorical features All right, so let's print it. So numerical features are these things, and the categorical features is ocean proximity. So we got this from our X-train data. Now what we are going to do is set up the pipeline for this. So first I'll say numeric transformer. So we are going to take all the numerical columns and perform some transformation on top of this. We have this numeric transformer is equal to create your pipeline. So this pipeline we have created from sklearn, so we have imported it from this sklearn.pipeline. So let me do this code and explain you what's exactly happening here. It's again the same pipeline code that we have used earlier for scaling and model training. Here we are going to use it for like few more things. So how we would do is create a pipeline, open and close your parenthesis, and open and close your square bracket, which is a list, and then mention your scaler, imputer, and everything. So this list is nothing but it has to go through a parameter called a steps. So the steps parameter is basically the list where we have been passing it. I think previously we didn't use this steps parameter. You can remove it and mention it, or you can have it, so it's not going to affect it. So this list that we are giving, it's for the parameter called as steps. So here you can mention what are the steps that numerical columns should undergo. So the first step that it should undergo is imputation. So I'll call this as imputer and pass this simple imputer, and within this simple imputer parenthesis I'm going to give this strategy as median. You can give mean or median for this numerical columns. I'll give this as median. All right, so let's put a comma, and now here I'm going to say scalar. Here we can initiate a standard scaler. So we are creating an instance of the standard scaler. So these are the processing required for my numerical transformer. Similarly, I'll copy this code, paste it over here, and instead of this numeric transformer, I'll call this as categorical transformer. So here imputation. Again, I know that in this data set, categorical columns doesn't have any missing values, but as I said, you can even use this code for a different data set where both numerical columns has missing values as well as your categorical columns also has missing values. But we know that we replace the missing values in numerical columns with median, but in the case of categorical columns, the missing values should be replaced with your mode value, which is your most repeated values or most frequent values. So we can use this parameter called as most frequent, and simple imputer knows this. So yeah, maybe let's complete the other thing as well, and I can explain this to you. So the next process that should happen for categorical columns is one-not encoding. So here I'm going to say one-not encoder that we have imported from sklearn.preprocessing, and say handle unknown is equal to true. Sorry, handle unknown is equal to, let's say, ignore. And I'll call this as numerical features preprocessing steps. This one is our categorical features preprocessing steps. Let me explain this once I complete this code. There is another like 2-3 lines of code pending. So here we are going to create our preprocessing pipeline. So let's create a variable called as preprocess. Okay, so we have preprocess is equal to use your column transformer that we have imported from this sklearn.compose. From sklearn.compose, we have imported this column transformer, and inside this column transformer, we are going to pass our numeric transformer and then our categorical transformer. So I say this column transformer, and we have this parameter called as transformers. So say that equal to open and close your square bracket, and similarly give these things. So here, let's say num, pass your numeric transformer, and then pass your numeric feature columns. Let's pass this numerical features. All right. I'll just call this as numerical as well, just for consistency. All right. So next I'm going to create this as cat. So pass your categorical transformer and then your categorical features. Right. So now let's understand what's happening. So the idea is simple. Numerical features should go through imputation and scaling. And categorical columns, we shouldn't perform scaling. So scaling should happen only on numerical columns. whereas where categorical column should undergo this one not encoding. So what we are doing is we are saying, or basically creating this pipeline where we are saying that numerical features should go through this imputation where the missing values are going to be replaced with my median value. So simple imputer knows this when you give the strategy as median, and saying that after imputation is done, replace, I mean, sorry, not replace, scale this data using standard scaler only for numerical features. And then we are creating a categorical transformer and saying, creating a pipeline saying that missing values in categorical columns should be replaced with most frequent value, or in other words, your mode value, and then they should be encoded with one not encoding. So again, as I said, please go through this one not encoding video. If you forget this, I mean, like if you forgot this, go through that. So that would be a good revision, where we just like, instead of performing label encoding where one value is turned into 0, let's say we have like class A of 0, B of 0, sorry, B of 1, C of 2. Let's say this is how we are encoding. So this is called as my label encoding. So instead of this, A will be labeled as into 3 different columns. So 0, 0 and 1. B will be labeled as 0, 1, 0. And C will be labeled as 1, 0, 0. So this is better than this label encoding, because this label encoding should be used for your ordinal categories where there is an inherent order in your categories, like movie reviews, good, average, bad. So there is an order in these categories, right? Whereas in the case of your inland or your less than 1 hour drive from your ocean or island, so there is not much order in it. So those types of categories are called as nominal categories. So whenever you have nominal categories, perform one not encoding, whereas when you have ordinal categories, use there's label encoding. So that's the difference, right? And just because this data set has the categorical columns as nominal things, we are using one not encoding. And this handle unknown is equal to ignore. What it means is, what if your training data doesn't have a fourth category, but your test data has a fourth category of D? So instead of throwing any errors, it's just going to ignore that error. So that's what this handle unknown is equal to ignore is going to do. So that's about it. So my numerical features should undergo imputation and standard scaling, whereas my categorical column should undergo imputation and one not encoding. And now we are stitching that together in a column transformer. So we are creating this variable called as preprocess, which is a column transformer, and passing these transformers, saying that this is the process that should happen for my numerical features. So this is the name that we are providing. And for this numerical things, this numerical transformer should happen. And here we are providing that these are the columns for which this numerical transformation should happen. And the next one is categorical columns, and here we are saying that for these columns, for these categorical features, categorical transformation should happen. So this is a much better scalable way, instead of you manually picking the numerical columns, applying some transformation, and then like in the next place you are like, let's say, picking the categorical columns and doing this. It is possible. You can, instead of doing this in pipeline, you can manually get these columns, perform this what you call imputation and one not encoding and so on. You can still do that, but the problem is when we move to cross validation and the hyperparameter tuning and so on, this should happen individually for like all these folds and all these different fits. So it becomes tough as we kind of like move to this model selection and your hyperparameter tuning or your cross validation. So when you have this in a proper column transformer and pipeline, this process is automated with proper configuration. Here, as categorical columns need a different flow and numerical columns requires a different flow, we can easily stitch these things together inside pipeline and create a column transformer. And that's the power of this. So I hope you understood about this. And this is, I think, a new concept that we are discussing. We have already used pipeline, but we are using this column transformer here only. So let me know in the Q&A section if you have any sorry, if you have any doubts about this, you can let me know in the Q&A section. I can like explain this to you if you have any specific concerns or questions about this. Okay, so this is our pre-processing pipeline that we have created. So we are not using this right now, we are only setting this up, but once we train the model, once we add it there, we will kind of use this pre-processing step. So this is our fourth step, right? So this is our data pre-processing. Next, let's move to the next step, which is creating a baseline model. So I'll say fifth is baseline model. So baseline model as in a simple linear regression model where we are not going to do much optimizations and like consider a lot of things. So I'll say no CV no tuning. This is basically to show what's the performance that you're getting for a baseline model, and after we perform this cross validation, how reliable score we can get, and after we do model selection and so on, how the score is improving. You can also skip this baseline model, but you wouldn't know how well the model is improved. So that's why we are creating a baseline model and then doing these optimization. So that's the purpose. I call this as baseline model, or maybe let's call this as baseline pipe. The baseline pipe is equal to, we again have to create a pipeline. Let's again use this steps parameter, and we know that the steps parameter is a list value, right? So here I'm going to pass two things. One is pre-process, pass your pre-process column transformer, and in the next step pass your model. These are pretty advanced stuff, and I think I'm explaining this in a simpler way, and if you are very clear with this, it's going to be really helpful for you when you're working on a more advanced machine learning pipeline compared to just simply training the model and evaluating it. So here what we are doing is, instead of just saying your standard scalar dot fit on your training data, and then doing this model dot fit on your data, performing this imputation and all that separately, we already have this pre-process pipeline using this column transformer. So we are creating another pipeline over here where the first step is pre-processing and the next step is model training. So when we call this baseline pipe dot fit, the data first goes through this pre-processing step. And if you come back here, the pre-processing steps as this numerical transformation and categorical transformation, which is imputation, scaling, and imputation and one-not encoding. You can also go ahead and add like other things, like if you want to handle your outlier values or even some other processing, you can do that as well. But this is basically a way of how we can combine multiple configurable things, where the important aspect is like how the flow is different for numerical columns and categorical columns. So that can be handled in pre-processing. And instead of doing these pre-processing and modeling separately, we first call this pre-processing step, and after that the modeling happens automatically. So those are the two steps present in this baseline pipe. So let's run this. So the baseline model we are considering this is linear regression, and once we get the metrics, we can move to model selection, where we would try linear regression, lasso, and ridge regression, and we also try random forest classifier and ist gradient boost classifier. So that's the process. So now we are going to pre-process the data and train the baseline model. So to do this, we should call this baseline pipe that we have created and fit this data with this X train and my Y train. Same way we would train a model with model.fit. Only difference is that it's going to go through a process called as pre-processing, and then modeling will happen, where the model will, this linear regression model will learn from this data. Let's run this and look at this flow. So this is the pipeline that we have created over here, the baseline pipe that we have created. Picked up this documentation, don't need this. Okay, so this is my baseline pipe, and this baseline pipe as this column transformer. So these are the two steps, pre-processing and modeling. So these are the two steps that we have. This, okay, right. So pipeline has two processes. One is pre-process and the other one is your linear regression model. Okay, so one is your pre-process and the other one is your linear regression. This pre-process is what you're seeing over here, pre-process. And then we have this linear regression model, and pre-process is nothing but a column transformer that we have created over here. And this column transformer has two flows, one flow for numerical columns and the other flow for categorical columns. And these are my numerical columns. You can simply just click on this drop down to see like more details. So first I have a pre-process column transformer, and that transformer has this two steps. One is numerical flow and the other one is like categorical flow. And after that we have this numerical column. So click this. So these are the numerical columns. So these numerical columns would go through a simple imputer where the strategy is median. Whereas in the case of categorical columns, which is this ocean proximity, the imputation method is your most frequent. Okay. Right, of course, we don't have any columns that has missing values, categorical columns that has missing values. So this is not going to affect any columns. But if you are working with a data set that has, let's say, 10 categorical columns, and out of that 5 categorical columns has missing values, so this is going to take care of that. And then for numerical columns, we do a standard scaling, and for categorical columns, we perform one-not encoding. So this is the advantage and the powerful feature of this. So we start with this baseline pipe. So this baseline pipeline has two processes, pre-processing and linear regression model. Pre-processing, which is column transformer, has two flows, one for numerical flow and the other one for categorical flow. This has simple imputer, both are simple imputer. This has median as the strategy, this has mode as the strategy, which is most frequent value. And after that it goes through standard scalar and one not encoding, and then we finally train the linear regression model, and the model is already trained. Now the advantage is, when you call this model for prediction, for inference, all these transformation would happen automatically. You don't have to manually again impute the missing values. You don't have to manually apply standard scaling. You simply call this baseline pipe and call this model.predict, and that would take care of imputation, standard scaling, and getting the prediction from your model. So that's another advantage of this. So now let's say train baseline pred. So I'm getting the prediction for my baseline model. Okay, this is my training data prediction. I'll call this as baseline pipe dot predict. Pass your xtrain. This is mainly for our evaluation of our baseline model. Let me put it this way. Evaluation of baseline model. So we have to do it for both training data and test data as well. Right. Similarly, we can get our test data as well, because test data metric is the important one, right? So note this, that this test data has not been used for training or anywhere. Only for final evaluation we are using this, and after this we will perform optimization. There also we won't use this test data. Only for the final evaluation we will use this. So we have trained baseline prediction. So basically, maybe I'll just like rename this, or let's maybe keep it this way. Right, so from the baseline model, I'm getting the train data prediction. Similarly, for test data prediction, I'm getting the predictions by passing X-test features, and here I'm passing my X-train features. Now we have to get the scores for this. Let me just quickly write this. We are going to get three scores: mean absolute error, root mean squared error, and R squared error. Maybe let's first start with root mean squared error, because that's the important metric for us. So I'll call this as train baseline root mean squared error, RMSE, is equal to root mean squared that we have imported from sklearn.metrics. First pass your true labels, that is your true house prices, which is y train, and then pass the prediction that is given by the model, which is this train baseline pred. Let's pass this over here. Similarly, we have to get our mean absolute error and R squared score. We have to update this to MAE, which is my mean absolute error. This should be replaced with R2, which is R squared error, and just replace this with mean absolute error, and this should be replaced with this R2 score. Right, the parameters remains the same, true house prices and the predicted house prices. So the train baseline pred and test baseline pred, basically as your model's predictions on what's the house prices, these are the actual values. You can also try and print the first 5 predictions. So these are the values that are predicted by the model. Whereas if you print the first 5 train data, right, so this is the actual values that is given by the model. This is the index. Don't look at this, just look at this number. So this is the price, but the model has predicted it this way. So this is the price of second house, the model has predicted it. So we are just like getting the score for this mean squared error, mean absolute error, and R squared error, and then we can simply print this. So I'll say I have this print statement. Maybe I'll quickly copy paste this. We are just like printing the values that we got: train baseline, RMSE, mean absolute error, and R2 scores. Let's run this. So root mean squared error is 68,433. MAE is 49,594. R squared error is 0.650. So R squared error should be lying between 0 and 1. If the value is closer to 1, then your model is like pretty good in understanding the variance that is present in the dataset. It means like for different house prices, your model is performing well. If it's closer to 1, if the value is like lesser, this value is not that much high, it's 0.65, it's not that much good, and this represents the error. What it means is, if your model is giving a prediction, it can have an error of 68,000, which is pretty high. Okay, so it's not like a very low number, so this is a pretty large number. Mean absolute error also does the same thing, but if your error is making larger errors, then root mean squared error gives a higher penalty. So what it means is, the difference is, Mean absolute errors treat all the errors in the same way, whereas if your model is making predictions um, in a larger scale, then those errors are amplified because we would square the values, square the errors, and then take a square root of this. So that's why we are doing this. And just because our model has this higher cap, our model can tend to what you say, it tends to make mistakes on that higher house prices of 500,000 and so on. So that's why we are using this RMSE, so that when it kind of makes errors on those top levels, your model is penalized more. So this is our train baseline metrics. Similarly, we have to get a test metrics. So this is only our train data. Now we have to get this test data. So I'll say a test baseline RMSE, R squared error, and then this is my test baseline metrics. Just like update this, all this train names with test names. So here also we have to update this with test. So this is my original house prices for test data. And here we have to update this with test data predictions that we got over here. Let's just like replace this over here. So instead of train baseline pred, say test baseline pred. So this is the prediction from a baseline model, but for test data. So let's run this. 70,049, 50,670, 0.625. The model is, I mean, the score is not that much different. So there is a chance that the model is underfitting. It's not able to perform well on our training data as well as on our test data. So now we move on to the next step, which is taking this data set and performing some optimization. So instead of training this linear regression, we are going to perform model selection with linear regression model, lasso regression, ridge regression, and a bunch of tree-based models, and try to see how well we can improve this model score. Again, it might not be that much high, but we would definitely be able to improve the score. So that will be the next step. Okay, so we are starting with this particular scores of 70,000 as our errors. I mean, 70,000 is not like that much bad, because the house prices can be in the range of 300,000, 400,000. I mean, it's still high, but it's not that much high compared to the scale of this thing. So there is not a single RMSE value where you can say this is a good score or a bad score. Your error value depends on the scale of your data. Let's say the house prices ranges between 1 million, 2 million, or 10 million. In that case, 70,000 error is very small. So always look at your target scale and then make a judgment of whether the score is high or low. So don't blindly say that if root mean square error value is less than 100, the model is good. If the root mean square value is more than 100, it's bad. So we shouldn't say this. This value depends on the scale of the target. Okay. So if your scale is in the millions, 70,000 is not bad. If your scale is 100,000, then your model is bad, right? This much amount of RMSE is bad. So always look at that scale and then make that call of whether his model is good or not, right? So now we move to the next step, which is sixth step. That is model selection and optimization. Let's continue this code here. I'm going to create a dictionary. So let's call this as models, and in this dictionary, the key will be the name of the models that we want to try, and the value will be the actual instance of these models. So let me just add a comment here saying models to try. So yeah, so let's create a key over here, and first let's say linear regression. Put a colon and create a value. So value is nothing but the actual model instance, linear regression. Put a comma, and now let's type in ridge. So this is for ridge regression. So we can import, so we have already imported this ridge regression. So use this ridge and also include this random state value so that we can get this same scores as we like try this multiple times. So this is the ridge regression. And next we can try for lasso. Same thing. So random state, and put your random state. So for lasso regression alone, we are going to add another parameter called as max iter and say 10,000. So basically max iter represents how many times, what's the maximum number of iterations the model should update its weight. There is a concept called as convergence, and again this is something that we have discussed in our gradient descent video as well. So model optimization, again, not this hyperparameter optimization, but their internal model parameters like your weight and bias. The model try to find this best optimum values. At this best values, the loss function value, the loss value or your error value is minimum. This point at which you get this best result is your convergence. Okay, so convergence you can think about as the point where your model is like kind of reached its lowest error or highest accuracy or performance. In lasso regression, we have discussed that it's going to turn off some parameters or basically weightage of some features. So usually what happens is lasso regressions needs more number of iterations compared to the other models. So here we say max iteration is equal to 10,000. So it means like it has to try maximum of 10,000 times to reach that convergence. If that convergence, which is that place where your model parameters are the best, if that place is reached at 5,000 iteration, it's going to stop there. It's not going to run for 10,000. It's just like a maximum limitations of how many times it can try. And this is like specifically for lasso, the convergence may not reach early. So we can just like add a maximum iter. And this parameter is applicable to other models as well. So whenever you get a warning in your model training saying that convergence is not reached, increase the maximum iteration and that would solve that particular warning, right? Now let's move to the next model, which is random forest. So I'll call this as random forest, and here let's create an instance of this random forest regressor. Finally, we are going to try this ist GB, which is a gradient boosting model, ist gradient boosting. Let's get this ist gradient boosting. So I have missed a comma over here. All right. Okay, run this. Now we are going to perform model selection, but we are not going to do a one train test split and evaluate on this. Rather than that, we are going to perform cross validation so that the score is like more reliable as we are going to do it for multiple folds. So I'll call this as k is equal to 5, the k fold value, and I'll say CV is equal to k fold that we have imported from sklearn.model selection, and within that I'm going to give this n splits. N splits is how many folds you want, which is basically your k value. So I'll pass this k here. So this is going to create 5 folds. We can shuffle this data. So it's going to create the fold after shuffling the data overall. So let's say shuffle is equal to true, and then random state is equal to random state. Same thing to make sure that when we run this the next time, the splits as the same data as the previous time. If you don't include a random state, every time your data is going to be split in a different way, and because of that the score is also going to change slightly. So we have this cross validation fold. Now I'll create a dictionary called as scoring. Scoring is equal to RMSE, and here I'm going to call this as negative RMSE. So I'll say NEG, which stands for negative root mean squared error. Basically your root mean squared error only, but we represent that in negative number. I'll explain this, but I need to complete few steps of the code so that I can explain that better. Let me first do that. Next one is negative mean absolute error, and then our R2. So R2 is not negative, so R2 is positive. So I'll explain this about like these negative metrics once we do this hyperparameter tuning, but just remember that we are taking negative of this root mean squared and negative of this mean absolute squared error, but R2 square we don't have to take negative. So this is the different scorings that we want from our cross validation. So basically we are going to perform cross validation on 5 different fold. For each fold, for like each iteration, let's say we would have 5 iteration. For each iteration we are going to get the root mean squared error, that is the negative root mean squared error, negative mean absolute error, and the R2 squared error. So I'll create a list called as rows, and I'm going to iterate over these loops. So basically we are going to perform cross validation where it happens 5 times, right? So you have 5 folds, so there is 5 iterations and you're going to get 5 different scores. And I'm going to iterate this over 5 different models. So first I'll take linear regression model, perform cross validation where the linear regression models runs in 5 iterations to get the 5 cross validation score, and finally it gives this mean cross validation score. That's the first iteration of the for loop. And in the next iteration we use ridge regression, again 5 folds of cross validation, and this process goes on and on. So that's the purpose of this for loop. So I'll say for name comma model in models dot items So models is that dictionary that we have created listing the name of the models as well as the instance of that model itself. So this is the name, this is the actual models instance. So we are iterating over this. So when I say for name comma model in model.items, at each iteration, name is going to take the name of the model, which is basically my key. So name takes this key value and model variable takes this instance value, the actual value. I can also print and show this to you. So I'll say print name and model. And you see, so this is the name that it is getting printed here, and this is the actual model instance that it is getting printed here. So we are going to iterate over this and perform this cross validation. So let me just remove this, right, and say pipe is equal to same way that we have kind of executed our linear regression based pipeline. So I'll say pipeline steps is equal to your preprocessor. First, the data has to be pre-processed with that imputation, standard scaling, and everything. So use that same syntax, same code that we did. The only difference is in model, it should be this model. So at each iteration, the pipeline is going to change with first linear regression, then ridge, lasso, random forest, and finally ist GB. So here I'll call this as model. So this model is the variable that we have from this for loop, right? In the next step, I'm going to create this scores. So I'll say scores is equal to cross validate. So this is also the function that we got from this sklearn.model selection. I know that we have been trying different ways of cross validation. The concept is same, but I'm doing this differently, and it's being done intentionally. So for the previous projects we have did stratified k-fold and things were different. I wanted to show this because I want you to learn these different forms of how you can do this model selection and cross validation and so on. So it would just like give you some experience on like different ways, and that's a good thing. So that's why. So first cross validation, pass your pipe, which is your estimator, and then pass your x data, which is x train, pass your y train, which is your training data. CV is equal to CV. Scoring is equal to the scoring dictionary that we have created in the previous cell with that negative root, mean square, mean, absolute error, and so on. N jobs, so this make sure that all the CPU cores runs for this multiple training of cross validation. So previously I think we used this stratified k-fold, we got the splits and we have iterated over for loop. So we kind of like iterate over different folds, got the predictions individually and so on. But here we can use this cross validate, which is automatically going to fit the data, train the model, and get the score. But I think in the previous case we did this by ourselves. We created a stratified k-fold instance, iterated over the for loop, manually created the folds within that for loop using the stratified k-fold that we got, then got the prediction, then got the score. But instead of that, we can also use a simpler way of cross validate. The reason is sometimes like doing that manually with this different steps of for loop would give you more control, but sometimes you can easily use this cross validate. So it's better to know like all these different versions, so that like you are aware about that. So this wouldn't give you much what you say control, as this is kind of like a more higher level function that does multiple steps separate, I mean multiple steps together. But in the previous video we did things separately, like splitting it, training it, and predicting and getting those test CV scores. So that is also like that gives you more freedoms. But as I said, I want you to practice like all these different versions, right? So that's about cross validate. So you give the pipeline, you give the training data features, training data labels, your CV. So CV is the k-fold that we have provided over here, scoring and job. So this is automatically is going to train the model, get the validation prediction. So what it's going to do is this training data will be split into 5 folds. So fold 1, fold 2, fold 3, fold 4, and fold 5. So when the model trains for the first time in the first iteration, this F5 will be your test data. Remaining 4 will be your training data. Second iteration, this F4 will be your test data. F1 to F3 and your F5 will be your training data. So this process just goes on and on. So basically you're training one model 5 times with these 5 different iterations, and you're scoring, I mean saving this scores here, the mean cross validation scores over here. Okay. And now we can also create a data frame out of this. So first I'll create this rows dot append. So this rows is a list. So I'm going to append this scores in this list in the form of a dictionary. So I'll say model, do it this way. So we are appending a dictionary to this rows list. So this rows is a list. And here I'm going to say the key is this model. First we give a model name, and then we give this CV scores minus of scores. This is because we use this negative versions, right? Negative root mean squared error, negative mean absolute error. That's why I'll say test RMSC dot mean, and then similar thing. Maybe I'll just copy this and paste. Yeah, so this would be my CV RMSC. This would be my CV mean absolute error. This is CVR2. So for each model's iteration, for each model's opportunity, we are saving this RMSE value, test RMSE, test MAE, and test R2. This should be MAE. So cross validation as like all these values. And then we have R2 score. I'll explain this in detail once I complete this part of the code. Then we say sort based on lowest value, RMSE value. We are going to create a dictionary out of this. So I'll say CV results is equal to pd dot data frame rows. So pass that list that we have created dot sort values. Yeah, sort values. So sort based on your CV underscore RMSE. I think we have already used this sort values once. Right. So now I can say print CV model comparison. So this is, yeah, CV model comparison. This test data, this test score is not based on your test data that we have created over here. This is not from this test data that you see over here. So this test score that you see over here is basically split from this training data that we provide. So this is basically what we call as a validation set. From this training data, a separate validation set is kind of separated, and these are the square of this validation set. The original test data, or the one that we have called as the global test set, only will be used at the end of this code where we get this final evaluation metric. So that's one thing to remember. So don't think that this test scores are coming from that global test bit. We shouldn't use that over here because that would lead to data leakage issue. Here I'll print this data frame. Okay, let's run this, and now let's understand this code. So this might take some time, few seconds, as 5 models is running, each running 5 times inside this cross validation. You can also increase this number of times by increasing this k. So now maybe in the meantime, let's understand this code. Let's say the for loop runs for the first time. When it runs for the first time, this name take the value of linear regression, and this model variable take the value of linear regression instance. Okay, this is just a name, this is a string, but this is the actual model of linear regression. Okay, so name is the name of the model, model is the actual instance of the model which needs to be trained. Now we are creating a new pipeline where the first process is the same pre-processing step. So we use that same pre-process, but here this pre-processing is not going to change as we have defined it earlier. Model is a changing parameter or changing variable. So at each iteration of this for loop, this model name will change. So first it will work with the linear regression model. So the first time for loop runs, this pipe has linear regression model in it, and cross validation happens. Next time it has ridge regression, next time lasso, and so on. Let's say first time pre-processing happens in this pipeline, and then we have this model as linear regression, and then we get this cross validation. What happens here is this cross validation runs for 5 times, as we have set up this k value as 5, and we pass this pipeline with linear regression model and pass our training data, test training data, and it would automatically split this validation set and get the scorings and so on. And scoring, it's going to get 3 scores. One is my RMSE, MAE, and R2. Okay, so these are the 3 things that it's going to get because we have provided the scoring dictionary over here. As this happens on this validation set or a test set, it automatically adds this parameters over here. Maybe first I'll show you how this scores would look like. Not sure if it would be like easily understandable, but let's see. Okay, so first time, these are my scores. Okay, so yeah, so first time, sorry, this is the fit time, score time, test RMSE, test MAE, all these things. So this one is for the last model, okay, because at each time this course is getting updated. If you see over here, linear regression happens, the linear regression scores are saved in this variable called as variable, and this rows list is being created. Next time ridge regression happens and the scores values are updated. Now they are not of linear regression but of ridge regression, and for the final time ist gradient boosting happens. So these scores you see over here are for ist gradient boosting, but previously the linear regression model and everything would have worked. So all these values are now stored in this list called as rows. So maybe I can print this rows list, so that would have like better information. Okay, so when the linear regression runs for the first time, we get the CV RMSE value. That means, let's say you have this 5-fold test RMSE. Okay, so it's validations test RMSE value. So you have 5 folds, so you have 5 different values, or maybe like 5 iterations, and you have 5 values. We take the average of this. So the average of this is basically given over here. You take linear regression model, run it for 5 iterations inside cross validation, get the average. So for those 5 iteration, root mean square average value is this 68604. For MAE, it's a 49667 and R2. And then for ridge regression, these are the average values. Lasso regression, random forest one is to GB. So this is what happens. To view this data better, we are creating a data frame over here, the one that you're seeing over here. Maybe I can just simply say CV results. That would just like display this in a better way, right? So we have the model name over here, CV RMSE here, CV MAE and CV R2. Now, the values that you see here are sorted based on lowest to highest. So we are sorting based on root mean squared error, not the other values. If you see this root mean squared error value, ist gradient boosting as the lowest root mean squared error. So it means like it's making lesser error in terms of root mean squared error. Random forest is next with 49,461. Next is ridge, lasso, and finally linear regression. So this is what we are interested in. We are trying to find the model that has the lowest RMSE value. So this is basically the concept. So how we are doing this is, we are iterating over a for loop with a different set of models, and each model has to go through this cross validation. And for each model, we save this mean RMSE value, mean mean MAE value, mean R squared value, and then we are saving the results in a dictionary, and then like saving this in what you call in this data frame. So here we shouldn't add negative, so R square should be positive. Basically, wherever you have used this negative, add a negative sign over here, but for R square don't use this, so that's why it's looking negative. I'll explain this, I'll come back to this negative part as I said when we are discussing about hyperparameter tuning, but this is the overall idea. Let me delete this. Okay, so now the basic idea is this. So we started with 5 different models. We have identified that in cross validation is gradient boosting gave us the best result. Again, it's not one single score. The score is more reliable because we ran this 5 times using cross validation, and is gradient boosting got the lowest score. These are R2 scores. Higher R2 score, better the model is. And yeah, here we are using RMSE as our primary metric, and that's why we have sorted it based on RMSE and not based on MAE or your R2 score. So that's the idea. So now let's identify the best model. I mean, we already know this is the best model, but if you want to access it specifically, you can just like do something like this. I'll say best row is equal to CV results data frame dot. I mean, it's already sorted, so we don't have to get this right. So I can say best model is equal to my CV results model. Oh, in the first photo. Okay, let me do it this way. So we have a data frame that has the results from our model selection process from different models. So here I'll say I want to find the row that is the less RMSE value, like the lowest RMSE value. I'll call this as best row is equal to CV results, which is the name of the data frame that we have created, dot sort values. And here I'm going to sort it based on CV RMSE. So this particular column, again, it's already sorted, so it's kind of a bit redundant, but let's keep it still. So if you print this best row, it's going to print the first row, which is SGB 48190, because what we are doing is making sure that the CV results is sorted by terms of your sorted by means of your RMSE value, and get the first row alone. So this ILOC of 0, that means like get the first row from this sorted data frame, and the first row is ist model, right? SGB model. So that's what you're seeing over here. From this row, I can get the best model name. So I'll say best model name is equal to best row of model, best RMSE. So this is your best score, best RMSE score. So I'll say best RMSE value. From this single row, I'm getting all these values individually. That is all. And now I can just like print these things. Best model based on cross validation RMSE. I'll just like simply print it using these print statements, right? So best model based on CV RMSE. Model is my istGB, which is ist gradient boosting, and the best RMSE value is 48190. The values shouldn't be higher, the values should be lower, because these are error values. Error values should be lower, then that means your model is performing well. But this is just like opposite in terms of accuracy. In the case of classification, we work with this accuracy, precision, all these things, right? So there, if the accuracy is higher, then we say that the model is good. Whereas in the case of regression, these are error metrics. Except for R2, don't look at R2, just look at this RMSE and MAE. So these are my error values. Accuracy higher means your model is better. Error value lower means your model is better. Okay, so that's why we are sorting it based on this CV RMSE and choosing the lowest value model. So SGB as the lowest model, right? So this is what we have identified from this model selection process. So I'll say best model is best gradient boosting regressor. So this is my best model. Now the next step is, once you have identified a model from the 5 models that we have chosen, we have to tune the parameters. Now this is with the default parameters. So you have like this learning rate, max depth, and other parameters are there for your ist gradient boosting. So we didn't give any specific customized parameters. Now we can perform hyperparameter tuning on top of this to see if we can improve this performance a bit more. Let's see if we can do that. So this is my 7th step, which is hyperparameter tuning. Now let's again create a pipeline. I'll say HGB, which stands for ist gradient boosting pipe, is equal to pipeline. And let's create this steps parameter, which is a list, and same thing, say your pre-process. This process doesn't change. So say pre-process and pass your pre-process, which is a column transformer. And then here we would give a model. So we have identified istGB as the best model. So I'll say ist gradient boosting regressor and just add random state alone. Remaining parameters we can tune. Okay, so this is my HGB pipe. Now let's create a grid of hyperparameters. I'll call this hyperparameters combination. You can also try randomized search CV, but this dataset has 20,000 rows, so it's not going to take that much amount of time even with this grid search CV. So for the earlier iterations that I did, it took like 28 to 30 seconds, so it should be good. Okay, param grid. So I have these values ready. Let me quickly copy paste this so that I'm not spending too much time here. Okay, so this param grid represents the different combinations that we have to try. Say for example, try it with learning rate of 0.3, max depth of none, and this max leaf node of 15, min samples leaf of 20, L2 regularization of 0.0. Next iteration, the model will try for 0.03, but for model max depth, it will take 3 instead of none. This will be 15, 20, 0.0. Next, it will be 0.03, 6, 15, 20, 0.0. So it's basically all these different combinations. It wouldn't leave out any combinations because we are going with grid search CV. Randomized search CV is like getting in between combinations, in between randomized values, but grid search CV is like performing all the combinations within this. And not about that, for each of these combinations, it's going to perform cross validation. So let's say one combination is 0.03, none, 15, 20, and 0.0 for these respective parameters. For this combination of is gradient boosting, it would run 5 times because our cross validation k is 5. Next time, it would only change this learning rate value 0.05 and then try it with max depth of none, 15, 20, 0.0. So this combination again happens 5 times. Next is 0.1. And similarly, now it takes 3, tries out like all these values. So all these combinations are tried in your grid search CV. Now, when you are calling this ist gradient boosting regressor, it would have this random state as one parameter and learning rate as another parameter. Learning rate would be, let's say, 0.03, and let's say we would have another max depth as parameter, the ones that we have mentioned over here, max depth. These are the name of the parameters, but if you look closely, we are adding this prefix. This is not actual model parameters name. Model parameter name is learning rate, but we are adding this prefix of model double underscore. This is because if you don't add this model double underscore and just say learning rate, your grid search CV will think that you are giving parameters that it should try for both pre-process as well as model. So instead of that, we are saying model. This means telling grid search CV that this parameter tuning that I'm doing is only for this model. That's why we use the name model over here. It's just to tell grid search CV that it's not for pre-processing. If you don't do this, it will think that this parameter is applicable to pre-process and model and it will throw an error. So that's why we are adding this as a prefix. But when you're training a separate model, you would just use learning rate max depth. You wouldn't include this prefix. So that's another minute nuance that you should remember. Okay. So these are the different parameters that we are going to try for our grid search CV. Now, let's create an instance of this grid search CV with bunch of parameters and the estimator, which is our HGB pipeline and everything. Now I'll call this grid search CV. First is our estimator. So estimator is your HGB pipe. So let's paste it over here. Next is param grid. So param grid is equal to the parameter grid that we have created here. And then CV is the cross validation that we have k-fold cross validation that we have created over here. So it's going to try those hyperparameter tuning for these different cross validations. So I'll say CV is equal to CV that we have initiated before. Scoring, here we can just give one scoring. So basically the ranking. So what it does is it tries to kind of do all these combinations, train the model on the data, find which combination give you the lowest root mean squared error. So that's the concept. But here we are going to use negative root mean squared, not just root mean squared, negative root mean squared error. But as I said, I'll explain this in a minute. So negative root mean squared error, and then n jobs. N jobs means like my CPU. So I'm running this on a Mac Mini M4. So this has 10 CPU cores. So n jobs is equal to -1, saying that these are several combinations of model training, right? So let's say that hundreds of model training happens. So that means n jobs of 1 says that use only one core of my CPU. So all the training happens one after the other. If I use -1, then it means it's telling my machine, it's telling sklearn that use all my CPU cores. sklearn won't use GPU cores, so only the CPU cores will be used. So -1 is saying use all these things parallelly. So this grid search will happen parallelly. It will try these model training parallelly for these different combinations from my 10 CPU cores. So depending upon your machine, your configuration, the amount of time this grid search takes will differ. If you have like larger larger number of CPU cores, this will be like faster for you. So this is grid search. Now this is creating an instance with this parameters and everything. Now we have to perform grid search CV. So I'll say perform grid search. So you have to say grid.fit, pass your X-train and Y-train. So this is going to take, as I said, maybe 30 seconds or more. But let's understand about this. So see this, five folds for each of 243 candidates. So what this 243 means is, if you do all the permutations and combinations for these values, there would be 243 different combinations that you can get for these numbers. And each of these 243 candidates has to do 5 folds, 5 iterations, because this is a cross validation process. So totally it's 5 into 243 times fitting process happens on your model, and that comes up to 5 into 243, which is 1215. So this is the number of times the model is learning from the data. So you simply call this model dot fit X-train and Y-train, right? X-train and Y-train. So this model fitting is happening. This is just like running once, but this is happening 1215 times. So that's the number of times grid search CV is going to happen. Again, this data set has 20,000 rows and just like 10 columns. So it didn't take a lot of time, but I think previously we worked with credit card score, credit fraud. Sorry, it's a fraudulent credit card transaction detection classification problem, where the data set is large with 30 columns and maybe 250,000 rows or something. It was like pretty huge, right? So there it took quite a long amount of time, even with randomized search CV. So this is the power of grid search CV, where it's going to try all these different permutations and combinations of 243 candidates. And because of cross validation CV of 5, it's going to try 5 folds for all these 243 candidates. That comes up to 1215. And after doing this, it's going to find which combination had the lowest root mean squared error value. And this is what we are going to understand and find now. So this we can print it, like what's your lowest grid search CV root mean squared score, and what's your best parameter value. So the score that you're seeing is RMSE because we have provided it over here, root mean squared error, but it's a negative root mean squared error. So this gave you the lowest root mean squared error value, and the best combinations is this. So when you use this L2 regularization value, so we have L2 regularization, minimum sample lift, leaf nodes, max depth, and learning rate. So when you use these combinations of learning L2 regularization of 0.1, learning rate of 0.1, max depth as none, leaf node 63, and minimum sample lift 20, you get the minimum or lowest root mean squared error value. So this is our best possible hyperparameter combinations. Okay. So this is how you can identify or optimize your model with the best parameters. You can also try to include more parameters, try different combinations, or reduce it. Maybe you can just like use ChatGPT to try out different combinations. But yeah, with these combinations, this is what we kind of like got. Now, we first performed model selection and we identified that ist GB is going to give us the best RMSE value. That means like the lowest RMSE value. And then we performed hyperparameter tuning, and the root mean squared error value even more, it kind of like reduced. Earlier we got like 48,000. It's not a large amount, but still it's we got like some difference over here, 47408. So this is how hyperparameter tuning helps you to find this best possible combinations. Now let us discuss about this negative root mean squared error. So let's discuss this. So think about the same process that we did for classification. For classification, we have used this accuracy score as our evaluation metric, right? And what this grid search CV does is find a combination that has the highest value. So a combination that can give you the highest score. sklearn always try to find the highest score, and it thinks that if the scoring is high, then it's a good model. So think about this in terms of classification. In classification, the scoring can be accuracy score or precision score or recall score or F1 score, anything. If these scores are higher, then that means that the model is kind of performing well, and we say that this is my best model, this has the best parameters, this gave me like the best values and so on. This is for classification. Whereas in the case of regression, we are not working with accuracy values, rather we are working with error values. Error values lowest represents best model, right? So here highest accuracy score means best model, whereas in the case of regression, specifically when we work with error metrics like your mean squared error, like this one over here, root mean squared error is a error metric, mean absolute error is also error metric. R2 is not your error metric. R2 value, if it's higher, then the model is good. Whereas in the case of error metrics, if the value is lower, then the model is good, right? Because what this error means is how much mistake your model is making. So you want lowest error values. That's the concept. Now what happens is, as I said, scikit-learn or sklearn, when we perform this grid search CV, whatever scoring you give, it can be accuracy score or it can be error. It would say that if I get higher value, the model is best. it wouldn't distinguish between this classification metric or regression metric, or in other terms, it wouldn't differentiate between this accuracy score or error score. So we just need to find a way to tell sklearn that you shouldn't look for high score, you should look for lower score. That's why we are using negative of this root mean squared error. Okay, so think about this. For one iteration, we get the scoring of 50,000 as our RMSE value. Now there is another iteration, we get 60,000 as our root mean squared value. Now grid search CV thinks that 60,000 value is larger, so it would think that this is my best model, which is something that we don't want. We want to invert this when we are using error metric. If I add a negative sign over here, in terms of negative signs, minus 50,000 is a larger number compared to our minus 60,000, right? Because like negative scale, the order just changes. Lower number means higher, higher number means lower, right? So simply, as I said, minus 50,000 is larger compared to your minus 60,000. Now, when you introduce this, let's say in one iteration we get minus 50,000 and in one iteration we get minus 60,000. So the scikit-learn library thinks that this is my larger number, so this is the best model. There are two things that are happening over here. It's like an indirect way of telling it that this is a error metric, you have to look at lower number. So instead of, I mean, because sklearn doesn't have this distinguishing feature between this accuracy score or error score, we just added negative scoring over here. Now it says that lower number is best because lower number is the larger one in terms of negative scale. So that's the difference. So the main idea is whenever we are using error metric, we have to tell scikit-learn in an indirect way that you shouldn't look for larger number, rather you should look for the lower number. So that's the reason why we are using a negative root mean squared error value, and the same reason why we have kind of like got this negative root mean squared error, negative mean absolute error, and so on. So all these scores that you would get from this grid search best score will be a negative number. If I just print this, the best score will be a negative number, which is minus 47408. But we have to interpret this in terms of positive, right? So we don't want to work with this negative scores. I cannot say that my model's error is minus 47,408. So we just like multiply this negative number with another minus sign over here. So this is something that we shouldn't overlook. Okay, I have added a minus sign over here. So this is going to convert this negative sign into a positive number, and that's why you're seeing a positive number over here. So this negative thing that we are doing is just to tell scikit-learn that don't optimize for higher value, optimize it for lower value. Just an indirect way of saying that. That's the reason in the cross validation also we have added this negative, and this neg represents negative for this error metrics. But R2 we didn't add this because R2 higher values means the model is able to understand the variance on the data set better. So higher value means better model. So that's why we didn't add like negative R2 in the terms of like cross validation. And if you see this, as the scores would be coming as negative, for our visual representation and our interpretation, we have multiplied this negative number with minus, and that's why you didn't see this negative sign over here. Okay, so that's the reason for it. So I hope you have understood this, but if you are confused around this part, like some of you may have still have some doubts about it, please let me know in the Q&A section, so I can just like give you some more examples and maybe like some calculations on explaining it better. But this is the overall concept, right? So now we kind of like found the best parameter combination. Now what we can do is we can retrain the model with these best set of parameters. I'm going to create a markdown cell, and this is my 8th step, and this is about retraining with best params. Okay, same thing. So same pipeline and everything that we add over here. So I'll just like copy this. I'm just going to update this name to saying like HGB best pipe. Instead of that, I'm going to say HGB best. Instead of this random state alone, I'm going to add more parameters, which are my best parameters, L2 regularization of 0.1 and everything. Let me quickly copy paste this. Let us put it over here. Pay close attention over here. I'm using L2 regularization equal to 0.1. That's how you have to give this. This is a dictionary. That's why you have a colon over here, but here it's providing the model parameters. So this is what we have identified. If you use 0.1 instead of 0.01 or other values, if you use this, you would get highest performance. So that's what we have tried to identify in this hyperparameter tuning, and other things remain the same. And now we train this best HGB on our entire training data set. This is actually an extra step that we are doing from this thing, right? You already have a best estimator. So if I say grid dot best estimator, that already gives you the best model that kind of scored this 47,408, but that would have been trained on this 4 folds, like one of those iteration. So your GBs, I mean, like all those folds, one fold or one iteration gave you the highest score, right? And that is this best estimator. You can simply use this best estimator as a model. So this is a trained model. You can use it for prediction, but we can retrain it with our entire training data set, because this only has your 4 folds as well. So this is just to train it and get this model on their original data set. There is another way to get this as well. In your grid search CV, you can simply do refit is equal to true. So when you do this, when you call this best estimator, it does this thing automatically. So it automatically retrains your best combination of parameters on the entire data set. But I want to show this to you in this step of what happens under the hood. So that's why I'm doing this. But basically what we are going to do now, which is retraining with this best parameters on our training set, can also be accomplished using this refit is equal to true. But I just let's just take a long route and do that manually. So I'm taking this best parameter values over here, and I'm going to train this. I quickly copy and show this to you. So it's pretty much the same syntax. So HGB best dot fit. So we call that and perform this fit operation on our training data and features and training data models. Sorry, I didn't execute this. Okay, so this is what I've given. Train best model on entire training data can also be done with refit true in grid search. Yeah, but let's just redo this. Now we found the best parameters, and then we trained our entire training data with this best parameters that we have provided over here, and the pre-processing step would have also been happened. The next step, we are going to perform our final evaluation. I'll say final evaluation. So this is my 9th step. Right, so I'll just quickly copy paste this code. This is the same prediction code that we have done earlier. Like you would use this pipeline to predict by passing your features, just like the way that we did in the baseline model. In the baseline model, we got this mean squared error, mean absolute error, and everything, right? It's basically like the same thing. So this is the prediction on training data. To run this, so you get a score of root mean squared error of 35,909, which is pretty good. But this is training data, so of course you're going to get lower errors, but we have to mainly test it on our test data. So test data metrics is the actual thing. So this test data has not been used anywhere. We didn't use this for our model selection. We didn't use this for our hyperparameter tuning or anywhere. So this is this rolled out set, or you can also call this as a global test set, which is untouched. So we haven't used this anywhere. And this is the final metric that we have to report as to this is the error that my model is making. And then we are getting this root mean squared error, mean absolute error, r squared error, and so on. So the root mean squared error is 47,169, mean absolute error is 30,947, and r squared value is 0.83. This is better compared to our baseline model. So baseline model, the linear regression model, was giving us 70,059 as our root mean squared error, and MAE was 50,670, and R2 is 0.62, but there is a lot of improvements. So RMSE and MAE error values have been reduced, your R2 value has been increased, so that is a good sign. There is not much difference compared to the default parameters. Default parameters also gave us similar values, 48,190, 32, and 0.82. Of course there is a difference, but it's not that much high. But you can also try adding more combinations and see if you can get a better output from this. But this is the overall process, and this is the final metric that we should report. So we started with this baseline model of linear regression. We performed model selection and finally found this HGB to be the best model for this use case, and then we kind of did this final evaluation on the rolled out global test set that has not been used anywhere. So finally, let's quickly draw a residual plot to understand how the model is performing. Same thing, same performance related thing, but just in a visual representation way. Let me quickly paste this code. It's a simple code to just do this scatter plot and then our distribution plot. Let's understand this. This is for this scatter plot, the one that you are seeing over here, residual versus prediction. Next, this residual distribution plot. is coming from your ist plot. So first let's understand this thing. Residual plot is an important way to understand the model's performance. So this is the plot size. Here we are plotting this scatter plot, and x-axis value is test final pred, basically what the model is predicting in this step. So we gave this x-test features and we got the predictions right. That will be your x-test, and your x-axis value, the one that you see over here. These are the house prices that are predicted by the model. And residuals is basically the difference between the y-test actual values and the predicted value. Let's say the actual value is 50,000 US dollars and the predicted value is 40,000. This is what my model is predicting. So I just like take this true value, which is 50,000, subtract it with my predicted value, which is 40,000. So the difference is, let's say, 10,000. So this is my residual, basically the one that we are getting over here, and that would be my y-axis value. So y-axis is the difference between my true value and the predicted value. X-axis is the predicted value. So this is my residual plot, and each dot represents one house. Okay, and just these are just like zero axis. X-axis horizontal line 0. So you see this blue color line over here, right? Horizontal line. So this represents that, and then we have the title, label, y label, and so on. So now look at this plot. If a model is performing well, if the model has very low errors, then that means your residuals will be closer to 0. If your model is making accurate prediction, your residuals is 0. Let's say your model's price is, your house price is 50,000 and the model is also predicting 50,000. So the difference would be 50,000 minus 50,000. So you would have the difference as 0, right? So when you do a residual plot, all the value will lie in the 0 axis if your model is making accurate prediction. But of course, our model is having an error of around 50,000 or 50,000, right? 47,000 root mean squared. So that means our model is not 100% accurate, or like our model is not perfect. So in this, if the values are closer to our 0 axis or the residual value of 0, then that means the model is good. If the value is spread out across this 0, then the model is not performing well. If you look at this part, the values are dense. That means in this space between the house price of, let's say, 50,000 and 25,000, or even for like 300,000, sorry, from 50,000 to 300,000, all the values are concentrated in the center. But as we move to higher price houses, there is a spread over here. Okay, so it's not concentrated around the center. That means in this space, the model is not making accurate prediction. And this is why root mean squared error value was also telling us when your model is making larger errors. So in these spaces, the model is making larger errors, and that's why our root mean squared error is kind of like bad. So it's not bad. It's pretty good for this particular data set, considering we have houses in this 400,000, 500,000, and so on. And this line also tells you that there is a cap and your model is not performing in that cap. So we had a cap of 500,000 for like the houses, right? Even there can be a house where the right price in real world would have been 2 million, but our data set has had a cap of 500,000. So all this would kind of influence, and then maybe a reason why our model is not performing well on this particular part. But this is how you have to understand this residual plot. So if your model is good, most of the values should be concentrated around the center. This is what this distribution tells as well. It's pretty similar. Now we are just like plotting this residuals using a histogram in this distribution plot. Here we can see more. What it says is what we have discussed over here. Most values are concentrated in the center. So this is the residual value of 0, and we have the peak over here. So this data is not, this distribution is not skewed. So it's like more values are concentrated in the center. That means the model is performing well and the residual is mainly concentrated towards 0. So it's pretty good, but still there are like points for improvement, but this is good for this particular amount of processing and other stuff that we have done. So this is this entire thing that I wanted to talk about. So first we started with the baseline model, and then we kind of like went with model selection and hyperparameter tuning, and then we evaluated with our test set. There is one more thing that we can do, which is building a predictive system out of this. So I'll call this building a predictive system. So it's again the same functions that we have created in our previous video, where a user can pass new house values, and then we would just like give them the actual, we would give this predicted value. So I have this function ready. It's pretty simple. So I'll just like copy paste this quickly. Right. So we have this predicted house price function. So for this function, you have to give your trained model, which is our HGB best in this case, the one that you see over here. So we give this particular model, and we provide this longitude, latitude, all the input features, basically nothing different over here. So we give this longitude value. Sorry, it was my dog is making some weird noises. Okay, so I'm giving this trained model. I'm giving this longitude, latitude, all this input features, housing, median age, total rooms, and so on, and representing like what's the data type to be. This is like a, I mean, an optional thing. It's not like that much important, but it's a good way to represent your code. So we are creating a function where it takes in the trained model as well as the input features. It's going to create a data frame out of this and then pass this to the trained model, get a prediction, and just like, and then return the model's prediction, the house prices value. So basically create a data frame out of this, pass it to the model, get the prediction, and return it. Now this is the example inference. Let's say there is a new user or there is a new house for which we need to find the house price. We don't know the price, but we have these details. So we have the longitude value, latitude value, housing median age, total rooms, total bedrooms, and everything. So near bay and so on. So we have like all these things. Now our model is already trained on all these information. Now based on that learning, it's going to give the house price for this new unknown data point that we are checking. Now I'm just like getting this. So here we are calling this example pred. So we are passing this example pred values. So basically, so we have this function, right? Predict house price. I'm calling this function, passing this trained model, longitude, latitude value, all this input features value to this predict house price, and this is going to return me the price of that house. Okay. So predict median house value for one new house, total bedrooms can be np.net. So this np.net basically says that bedrooms can have your missing values. So this function would basically handle this because this model HGB based also has that pre-process which has the simple imputer. So you can also give this total bedroom as a missing value as well. So it's going to work. So we pass this to this predict house price and it's going to call this trained model, get the price of the house and return it. And that returned house price is saved in this variable called as example pred. And then we finally print this. And then we round this value to 2 decimal places and then we print it. So if we run this, we get that for these input features, for the housing and like households of like, you know, this input features and so on, the model is predicting that the price of the house would be 4,60,493, or in other words, 460K is your house price. So this is how you can build a predictive system out of this, where you can give a new data point and your model is going to predict it. So I hope you have understood all the things that we have covered in this, and this I mean, to be honest, contains a lot of advanced stuff, but I'm sure that you would have learned all the things that we have covered previously in the previous sections of this course. So you should be good with all the content that we have covered today. Just please practice this code line by line. Just try to understand this better, and you, as you practice more, you would automatically remember all these steps, all these functions, and so on. So before wrapping up, I'll just like quickly give a recap. Again, not a detailed walkthrough, but a recap of what we have done so that it will be a good revision for you. This is the process that we have taken. First is exploratory data analysis, and then we pre-process this where we set up our pipeline with column transformer pipeline and all that. We created a baseline model with linear regression, and then we performed model selection with 5 different models: linear regression, lasso regression, and ridge regression. Performed a tuning with grid search CV, and then we performed final evaluation on our global test set. And finally, inference is basically our predictive systems that we have built. So this is the flow. This is about importing the dependencies. This is setting up the notebook level configuration. How many columns the pandas should print and what's the float format, whether it should be in scientific format or decimal places and so on. And this is the format for your Seaborn plot. This is the font of your title, X label, Y label, and so on. Random state value, CSV path, target column. Again, the important aspect of this notebook is if you are working with a different data set, different regression data set, you should be able to use the same notebook with some minor tweaks here and there. And of course, the CSV path names, target column, and maybe if there are some places where we have hard coded some column names, you can simply use that. So for that particular configuration, we have this. Then we loaded this data using pandas.read CSV, understood the shape of this data frame, yet columns, and this is the column details that we got from Kaggle. Basic info, and we understood that there are some missing values in this total bedroom columns. We separated numerical columns and categorical columns in a list, analyzed it, and we also checked that there are no encoded missing values present in the data using value counts. Also, there are no duplicate values. We gone through this describe of this data, descriptive statistics, seen the found plot of this, and also the distribution of this. And the main important takeaway is that this data set has a higher cap, so your model may not perform well in this because it doesn't have much information. Model, I mean, like house prices in the range of 500,000 be present, but the input features will be very different. In real life, the value can be 2 million, but the data set would show that it is 500,000. So the model would not be able to distinguish those things. So there is a chance that the model wouldn't be able to get some values properly here. And then yeah, distribution plot, outliers plot, but this represents the actual value. So we didn't handle this. Correlation heat map also, this may affect our baseline linear regression model, but as we move to our tree-based models, this wouldn't be a bigger issue as tree-based models are not like kind of sensitive to the highly correlated columns. So we captured all our insights from this EDA and all the pre-processing steps and evaluation steps, and then we performed the data pre-processing with this, mainly with this pipeline that we have created. So your numerical features should go through a different flow, your categorical features should go through a different flow, and then we perform this column transformer with this your numerical columns, categorical columns. We created a baseline model without any cross validation or tuning. So we got this root mean squared value, which was pretty high over here, the test root mean squared value. Then we performed model selection with these 5 different models, performed mainly cross validation, got the scores, and we seen that as we are using errors, we have to go with negative scores. R2 score higher is better, so we didn't use like positive over here. Performed model selection, and we found that KISS to GB is the best model because that gave us the lowest root mean squared error. Finally, for this is gradient boost, we performed hyperparameter tuning with these combinations with scoring as negative root mean squared error because this is our primary error metric for this particular use case. It's not like you have to use this root mean squared error for all the regression problems. For this particular use case, this is better. So you can do your research and understand like for which use cases, which scoring should be done. And then we performed this grid search. We found the best combinations, retrained our best, retrained the model with best parameters, and then did our final evaluation with training and test. And there is of course a good amount of improvement from our baseline comparison. And then we draw this residual plot, residual distribution, and so on. And interesting thing, we also built a predictive system where we can give these new values and the model is going to predict the price of those. So I hope you have understood all the things that we have covered in this. If you feel like this, I mean, this video is larger, maybe do this in parts. I don't know. By the time you are watching this, you already would have like gone through this, did this hands-on. So that's all good. And if you have done this, that's pretty good. So it's like a pretty long use case, and that's good that you have done this. And maybe try out different regression problems and see like how you can, in a very good way, build regression problems. I just want to add one more thing over here. There is of course things that you can try to improve this model's performance. Just doing this itself like took so much time, so I'll just like add this in the markdown. So once you complete this course, once you have more time, you can just like try out these things that I have did here. So you can perform some more feature engineering, you can try like XGBoost or other models. This can, there is a high chance that this feature engineering and other steps can reduce your root mean square error even further. Maybe try these things once you complete this course. Once you have time, you can try this as well, but again you can move to other projects, but later when you have time you can come back here. So that is all from my side for this video. I'll see you in the next project, and if you have any doubts, let me know in the Q&A sections.